Should be now.
Really that bad?
Yeah, like, for us anyway, we don't, it was basically you had 2.4x plus c equals 9.4x times quantity of 3.4x plus 2. And we had find c. What does c equal? And I'm like, you're throwing in 2 letters. They barely understand one.
Right?
Okay. Hi.
Hi.
Are you ready to do math?
Let's do it.
Okay. Well, what I thought we would do, I'm recording on Zoom right now, so I thought we'd take the time to just do some quick introductions, to share your name, where you're from, and what you're teaching right now. I know we're all teaching kids, but what content and what. Do you have my kids? So I'm Chris Walcott, and I know all of you except Olivia. So I was so happy to see all the names on the list. So I'm really happy that you're all here. The reason I'm here is we received a grant from the state to provide professional development that encourages STEM education in the school. So one of our secondary goals is to hopefully convince some of you who aren't licensed in middle grades mathematics to go ahead and test for middle grades licensure. For the other teachers, it's just to build content knowledge. This summer, we're doing this course in math. Next summer, we'll be repeating this course and adding the science course. So if you're interested, keep that in mind. For those of you who, well, you might be doing monthly meetings, there's an incentive also. And I don't know, since some of you already have or you used to have middle grade licensure.
I am middle school language arts.
You're middle school, so you could do middle school math. Oh, you could do middle school. Okay, if you decide to sit for the exam and pass it, there's a stipend that you get, a cash stipend. It's either $500 or $1,000. I'll have to double check. So it has to be a license that you don't have. So if you have math, you have to try for the science. But if you're elementary or another middle grade content area, then you can do the math and get that stipend. So that's the main thing. And I'll double check the amount. Okay, so let me see. This is kind of backwards, but that is Adam. Okay, we'll start with Adam and just go around.
All right. My name's Adam. I teach at Edinburgh Middle School, 7th and 8th graders. Yes.
All right, I'm Tabitha Cole, and I teach at Shelbyville Middle School, and I teach 6th and 7th grade algebra, and then in 7th grade.
Are you in the same room where I observed your student teaching, or
You're
close by?
close. I'm like
Okay.
in the bathroom separate.
I can find you.
Yes, you can.
Okay, yeah.
I'm Greg Scudder. I teach 5th grade at Greensburg Elementary School. Beginning of the year, we started out all grades, or all subjects, and then last 9 weeks we switched to subjects. So I'm teaching math and history, and next year I'll be teaching math only.
I'm Gavita Hartman here in North Allegheny County, 6th grade teacher.
And do you teach do you departmentalize them all?
No, not this year.
Okay.
Zachary, I teach first grade at Parkside.
And do you don't, not in first grade anyway, you wouldn't departmentalize, right? You teach all the content.
Yeah.
And Olivia Kane. I work at Reading Elementary in Seymour, and I'm a Title I instructional coach for literacy and math.
Awesome. Okay. Well, thank you for doing that. I know that's really awkward. When I was sitting at home in front of the laptop recording the first session, I felt completely stupid, but I imagined all of your faces. Okay, so as you probably guessed, we're always going to use the modules as the roadmap for the class. So I thought what I'd do is just start out with that today and see what we have to do. So those of you in attendance here today, you don't have any attendance tasks at all. No summary, nothing. Only those, I don't think anyone joined live, but those of us who are not here will be watching the recording and doing that the summary to turn in as well. What you'll find is if for some reason you want to go back and listen to the recording, there will be a link right there on the word link. So you can do that. And then also the slides that I'll be going through today are already linked here. Let's take a look at the slides. There will be videos in Khan Academy, again, for you to watch, and there'll be some sort of discussion forum that you need to respond to there. Does everyone understand my thinking about why we're looking at the Khan Academy videos? Does that make sense to you? Okay, I think they're really high quality. And I think too often we surf the internet and we find strategies and suggestions from those who may not adhere to the best mathematical practices. In Khan Academy, that doesn't seem to be the case at all. Oh, hi, Sally. Well, we just introduced ourselves. Can I flip this so you can, we're recording too. Okay. Just tell us your name and where and what you teach. Do you see yourself on this?
Yes, I do.
Okay.
I'm Samantha Parker. I teach at MSD Decatur up in Indianapolis, and I teach life skills grades first through third this year.
Okay. Thank you, Samantha. The important thing that I wanted to mention that you need to know is if you decide to take the licensure exam in middle grades math, there is a stipend available. It's either $500 or $1,000 if you take and pass the assessment. So that's one of the sub goals of the grant that we have. All right. So all those links will be there, and those will be there. I'm not going to close this site. So if you decide, well, maybe next spring I'll take the test and I want to study, you can go back to the site and click on those links and get to the videos to use those to study. And then we are going to start a problem at the end of class. We probably won't be here the entire time, but I want to get you started on the problem. You can work together and collaborate, get some ideas going, and then that will be the problem that you turn in for this week's problem solving. This is a 6-week course, and so that means next week you will get your problems for midterm. Isn't that crazy? It's going to be a small problem set, so don't expect, I'm thinking at the most 5 problems for you to solve. And when you solve them, you do need to kind of make clear what your strategy is when you turn in your work. But you need to choose one of those problems to teach. And what I'd like you to do is you can use any type of technology you want to record that teaching. So if you have a screen sharing technology where you can do a capture and have like a voiceover with a PowerPoint, if that works, that's fine. If you want to use your cell phone and videotape yourself, that's fine. But those videos will be shared with all of your classmates, and your instruction will be key to a part of the final. So let me just say that if you watch all of your classmates' lessons, or little mini lessons, you're going to do very well on a big chunk of the final. Hint, hint, hint. Okay, so that's why we're doing that. It gives you a chance to share your strategy, and perhaps someone else in the class might do the problem completely different, and that really benefits that person because then they have their strategy and they're seeing you teach the strategy that you come up with.
Is there like a minimum, maximum length of the video?
I'm thinking
Depends on the problem.
it does depend on the problem, but I'm thinking if you go much over 5 minutes, it's probably too much. It should be, you're teaching a strategy for that particular problem. Okay. So next week, we are actually having an on-site meeting, I think is so I will, if you're here, you'll have information in class. If not, it'll be recorded. You'll have your problem sets, and I'll give you more details. What I think I'm going to do, I'm still weighing the options, but since we're working off this Gmail account to submit your assignments, what I think would work is to upload the videos to YouTube as an unlisted video. And when they're unlisted, no one can search and find it. You have to have the URL for that video to get to it. So probably what I'll ask you to do is once you record your mini lesson, is just upload it to YouTube, make it unlisted, and then you'll just paste the URL for your video into your final. Unless you have a way that you think would be better than that. I can't come up with one right now. There is a learning management system at IU now, and you all have access to it, but I wanted to make sure that we didn't waste time learning how to use that. So that's why we're using the Google Slides, and I think it'll be fine. Okay, any questions about the structure of our remaining 5 weeks, or any concerns about the work, or any questions about the assignments? Okay. So just always go back to the module and follow it from top to bottom, and you'll get through everything that you need to go through. All right, so that leads us to what I want to talk about tonight. Okay, so we're going to talk a little bit about problem solving and mathematics. For some of you, you might have heard some of this stuff before. I tried to, even for students I've had in the past, I tried to embed a little bit of new in this so you wouldn't be bored. But I want to talk about what it means, first of all, what it means for a task to be a problem, and then what it means to problem solve in mathematics. So when you think about the word problem, outside of mathematics, it usually has a negative connotation. We don't want problems, right? So when we think about problems, if you have your checkbook doesn't balance, that's a problem. It's in the middle of the winter and it's -4 and your heater isn't kicking on, that's a problem. So that's, I think, an issue that is interesting, because when we engage kids in problem solving and they hear the word problem, it gives you that feeling of, oh, it's a problem. It's going to be something that I don't want. And Webster says that in mathematics, anything required to be done or requiring the doing of something is a problem. Okay, that's clear as mud. And then the second one is a question that is perplexing or difficult is a problem. So those are the two definitions that Webster gives. All right, but what we're going to think about in terms of problem is that there is some mathematical task, and in order for it to be a problem, there's not a clear solution path that's immediately evident. Okay? So for us, if I give you the task of finding the product of 2 and 5, is that a problem? No, because most of us, we don't have to think about it. We don't think about what kind of operations involved. We don't think about what it means. We know it's 10. There's no thinking at all. What if I gave you a task that involved, hopefully I'm not tricky with this one, collecting data over a 6-month period for the average temperature every day over a 6-month period, and then I ask you to find the average of all those temperatures over 6 months. Is that a problem?
It doesn't seem like it.
Probably not for you guys, because you understand what average is, you have that background. There's a lot of work involved, right? Because you're going to have to figure out how you're going to average the daily temperature. They're going to have to find a way to store that information. And then once that 6 months of data is collected, how are you going to average them together? With technology, it becomes not a problem at all. If you know how to use Excel, for instance, you can just create a worksheet, click a button, and it'll give you the average, drag it across the cells. So yeah, that wouldn't be a problem for us. But what about for a 2nd grader? Probably so.
That's a
Yeah.
pretty big problem.
Yeah.
I was thinking 2 times 5 would be a problem.
Mm-hmm. Right, so what is a problem depends on who's doing the math, right? For some, it might be a problem, for others, it might not be. And then there can be a variety of forms. When you think of the word problem, a lot of people automatically go to a word problem, but that's not the case at all. It can be a raw computational problem. I might ask you to, if I give you a problem like 121 divided by 6 and tell you that you have to solve that mentally, that could be a problem if you don't have the ability to write it down or to use a calculator. So it's all about context and who's being asked to do the mathematics, whether or not it's a problem. But it could be an equation, it could be a computation, it could be a word problem, but it also could just be making sense of data in a graph table chart where there's maybe very few words involved. Making sense of what's going on with the trends. All of those can be problems. Okay, so we hit on this a little bit, but what other kinds of factors could determine whether or not a task is a problem? We said it depends on who's doing the math, right? What else could it depend on?
If you know, like, formulas or algorithms that go along with
Background
that.
knowledge.
Background, yeah, prerequisite knowledge, exactly. Anything else?
I didn't think about like my English language learners, so.
That's a good point, yes. Right, can they even make sense?
Everything's a problem.
Yeah, some of them. Yeah, so if you have a context where it involves a situation that they have to make sense of, then that's going to be problematic in nature. What we take for granted as being a given may not be a given for them. They might have to kind of draw a picture of what's happening and try to figure it out that way. Yeah. Anything else? I think the only thing that I would add, I think goes along with what Zach shared about knowing formulas and things, if you have technology available, you know, that can take the problematic nature out of the situation. Sometimes that's good and sometimes it's not good, right? So all of those things play into whether or not a task is a problem. So on a test, let's say that you're going to test your kids and you allow calculators, and you want to test them on whether or not they understand computation with fractions. Right? Are you really testing them on computation with fractions, or are you testing them on how they're able to use a calculator to find the answer? So keep that in mind, and that's okay if that's your objective. You want them to be able to use a calculator. The example about the average temperatures over 6 months, if your goal is not making sure that they understand how to add all of those numbers together, then introducing a calculator in that situation may be perfectly fine. You want to know if they know what to do with the numbers, not that they know how to add that many numbers together. All right, so in terms of problem solving, what we're going to be talking about is a requirement that students are given a more active role in doing the mathematics. So we're working towards being facilitators in the classroom, where we're providing supports for the students, but the students are really taking the lead. And that's a very hard thing to do. It takes a lot of time, it takes a lot of patience on the teacher's part. Oftentimes you have to behave in a way that is kind of uncomfortable to you, because as teachers we're usually giving and nurturing, and you have kids who want you to give them an answer or tell them what to do, and you have to back away and not do that in order for them to become true problem solvers. And it is not the equivalent to difficulty. Solving a problem doesn't mean that the problem itself has to be difficult. It's just that the strategy used to arrive at the answer is not clear-cut, right? Okay, so this is what the National Council of Teachers of Mathematics said way back in 2000 about mathematics education, what should come out of programs. So they want new mathematical knowledge to come out of problem solving. What we typically do is we teach the new knowledge, and then we use the problem solving for the students to apply the new knowledge. But NCTM says the problem solving should generate some new knowledge. It shouldn't just be an application of what you've already taught them. Now, that doesn't mean that everything you do in the classroom has to be that way, but students should have an opportunity to build some new knowledge out of their own problem solving. That the problems themselves could arise in other contexts, so it doesn't have to be mathematical. When you think about integrating across the curriculum, oftentimes there are mathematical problems that come out of science content, right? And even social studies content. Think about how much data is shared in social studies classrooms and how kids can make sense of that data. That's a social studies context, but mathematical problem solving. Apply and adapt a variety of appropriate strategies to solve problems. Moving away from, do what I do in the way that I do it as a teacher and letting the kids use alternative algorithms and things like that. And then this is the big change that they suggested back at the turn of the century about reflecting on the process of solving problems. So having students do things like justify their solutions or provide rationale for the strategies that they use is just as important as doing the math itself. So giving them opportunities to communicate that is really important as well. It's not just about getting the right answer, but it's about growing in their own understanding and being able to start knowing what they need to solve the problems.
I feel like being able to express that is more important than being able to, actually do the problem correctly.
And that's the hard part.
And then when you're walking through it, you can say like, okay, I see where you would think this, but this is why, this maybe didn't work out the way you thought.
Yeah, and that's hard. I thought you would find this interesting. I'm going to read it to you because I was going to put this on the full screen, but I'm afraid I'll lose my, maybe I won't. I'll try it. See a little bit better. Okay, so this shows some school kids back in the 19th century. I don't know exactly what year. And it's kind of blurry here, but you see there's the teacher, it's a man, and they're dressed, they have some interesting clothing on, but there's a chalkboard in the back. And on this chalkboard in the back is this problem. 10 squared plus 11 squared plus 12 squared plus 13 squared plus 14 squared, okay? And I'll read the text of this. It says, 19th century village school children depicted in the picture are clearly engaged in problem solving. If we take a closer look, we see that the problem they are trying to solve is the following. Calculate 10 squared plus 11 squared plus 12 squared, 13 squared, 14 squared over 365. It appears that the students are asked to perform this calculation mentally. And we're making that claim because none of the students are at the chalkboard and no one has their own slate trying to compute. You can see that the kids are kind of pensive as they're standing there. All right. The trick on which the teacher has based the task lies in the fact that 10 squared plus 11 squared plus 12 squared equals 13 squared plus 14 squared, which also equals 365, okay? Once these equalities are established, it becomes easy to perform the division and obtain the result 2. But to come to this realization is not that straightforward, even for a student who has memorized the squares of all the numbers between 10 and 20. Even if one calculates the sum of the first 3 items and arrives at 365, it is easy to miss that this coincides with the denominator. It is likely that students would then simply carry on adding 3 squared equals 169 and so on. I don't know if I copied the rest of it, but you get the idea. So there's a trick. This is a mathematical trick, right? This ends up being 2 because the trick is that these 3 squares equal, the sum of these 3 squares equal the sum of the last 2 squares. So it's a sequence of squares, consecutive squares, and because they're equal to 365, then we have 2 365s divided by 365 would leave us with 2, right? Is this a problem? We don't know exactly how old these school children are, but I would guess maybe 11-ish, 12-ish.
See, they thought it was a problem. When I looked on their faces.
Yeah, yeah. If I were to give you this, just hand it to you, would it be a problem? Would you know what to do? What would you do?
I would have calculated all the squares and added them together and then divided by this.
Okay. Definitely not a problem then. You have a clear solution path in mind, okay? What about the added element of doing this mentally without anything to keep track of your calculations?
It's a little more problem.
That's a little more of a problem, okay? All right. Do you think about your own kids. If you gave them this problem, would they even consider thinking about finding the sum of the first three and the last two? No.
They would immediately ask for a calculator.
Yes.
Okay. All right. So what would, if I told your kids to find the answer to that problem without using anything but their minds, what would happen?
Some of mine might say to.
Just because.
Just randomly.
Yeah.
To.
Would they have a path at all?
Said few, my fifth graders probably would, majority, they would melt down.
Right. I agree, because it's a stretch to think. Now, maybe these school children had some sort of lesson in the past that leads them to look for those kinds of patterns. But in general, if you were just to hand this problem to a kid and say, find the answer mentally without using any paper and pencil, without using a calculator, they would just look at you and say, huh? How do I do that? So they don't even have a way to start it. So when you think about problem solving, on one hand, if I give them the constraint that they can't use any materials to solve this problem, it becomes impossible. But if I just hand them the problem, it's not a problem at all. So that idea of placing a constraint on the situation may take something that's not a problem and make it into a problem, okay? Or beyond a problem. All right, hang in there with me. There's a reason why I brought this up. Okay, so here's the other, this is like the follow-up to that. So at the beginning of the lesson, Miss Pinkowski showed the students the reproduction of the picture that we just looked at and formulated the problem set there. She asked the students to solve it using a calculator and then think how it could be solved if they had to do it mentally, assuming that they already knew the squares of all the numbers between 10 and 20. Okay, so think about that. So she's doing something different. They have the problem, they use a calculator, and after they arrive at a number, they're thinking about the numbers that were part of the problem. Why do you think she would do something like that?
Then it makes the problem that wasn't a problem now it is a problem because now we have to figure out the measure.
Okay. So it's sort of like they're working backwards, right? They find the answer. Now I got to figure out how the numbers in that problem contributed to me getting that answer, and could I figure out mentally how that calculation would work? Okay, so then the class provided the answers. The teacher remarked that the problem was based on an arithmetic trick, but then, feigning hesitation, asked if it's really a trick after all. Are there perhaps other similar numbers? The question was, can one name any other sequence of 5 whole numbers where the sum of the squares of the first 3 would be equal to the sum of the squares of the last 2? This is brilliant. Think about this. So here's this problem where Miss Pinkowski or your students, if handed it, would more than likely either use their paper and pencil and calculate an answer, or go to a calculator and find an answer. It would mean nothing to them except plug it in and get it done. She's taken that and allowed them to use a calculator to find the answer, and then says, now go back and think about how could a mental calculation help you arrive at that answer. And then poses the problem, is this the only sequence of 5 consecutive squares that would have this property where the first 3, the sum of the first 3 would equal the sum of the last 2? Is that a problem? Yeah. I like Miss Pinkowski. She's awesome. But that's what we can do. So it's not even necessary for us to pick a problem that we necessarily think is a problem that would work well with our students, but think about how we could use it in a way that would work with our students. Okay? What do you think about her question?
I'm interested to know.
Okay, I want to know. So everyone is sort of close to another person. Just talk for a little bit. Remember, this is a pass-fail course. You can take all the risks you want. It doesn't matter. Okay? But see if you can come up with another set of 5 consecutive squares where the sum of the first 3 is equal to the sum of the last 2. Just try something, and I'll give you a few minutes, and we'll talk about it. Make a conjecture first. Who thinks there is at least another one? There has to be. Okay. All right. So maybe there's another. Sequence of 5.
Yeah. Yeah, that's what I was thinking, but then I started basic.
Like
Right.
even if you start out with 1 plus 4 plus 9.
Squares of 1, 2, 3, or less, squares of 4 or 5. Yeah. So I wonder if it matters that 2 digit numbers.
That's awesome.
And then that it starts with 10 and out.
Yes.
So
Double numbers, of course.
that it would. 12.
It's messed with.
You just have to double, but you have to double the denominator too. Right? Well, I guess not. It wouldn't be. It should still be.
Anything
Yeah, it would still be.
is
Where'd you start? Did you start at 2? At 2?
Those of you watching the recording, try this at home, please. And you'll benefit from our wonderful insights in just a few minutes.
If someone has a revelation, just blow it out. Anybody noticing some patterns as you're trying the numbers?
I got it worked out.
I did too.
14, 16, 14, 16. Oh, no. Down here, but yeah, 14, 16, 14, 16, so it worked. I doubled the original set. So instead of 10, I used 20, 22, 24, 26, 28, for my 5 consecutive numbers. And it works.
But are those squares?
Yeah, it's 20 squared, 22 squared. 24 squared. It works.
So you use 20, 21, 22.
No, I just doubled the original set. So instead of 10 square days, 20 square.
Yeah,
Oh,
because that's what I thought too, but then it's not consecutive.
Yeah, I like 22. But that one-
Oh, yeah, you did
Because
that.
that's what I was thinking too, but then when I tried it,
I didn't-
Oh,
because they're not consecutive.
that's right.
Consecutive multiples of 2. so.
That's interesting though. So, I mean, if that happened in your classroom, you could ask students, do you think that would happen if I multiplied the original set by 3 instead of doubled it? And see if they, maybe you can find other patterns that would grow out of it as well. Did anyone find anything that looks promising?
You can probably do this one day.
Yeah. What about technology with this? Can you think of any way that you could use technology in a way that could help students investigate it without getting them to the point where they're so frustrated, no one go on? I was thinking like with a spreadsheet, we could probably do a spreadsheet and change the numbers quickly and have them squared and have them sum. And then you could get 2 columns and then you just check quickly to see if they equal. Because this isn't about the computation at all, right? We all agree about that. We can do the computation all day. It's not going to help us. It's about finding something that helps us get to an answer. What did you see happening when you would try numbers? Why wasn't another five number sequence of squares working? What was happening?
Because,
The sum of the first 3 was becoming bigger than the sum of the last 2.
Yeah, so it wouldn't, you could just keep going and that probably always see that, right? Did anyone try anything smaller than the 5 that we had?
yeah.
Was it the same thing?
1, 2, and 3, and 4, and 5, but it was on the other end of it. So I wonder if that problem is in the middle
Right.
of those 2 things.
Okay.
So the sum of the first 3.
Like that's
Smaller
the
than the
point
sum
that
of the-
changes.
So something's going on there. Okay, so I want to pull this back to the slide before. I'm going to ask you a few questions. Just get your brains going. There's the problem again. So we had 10 squared, 11 squared, 12 squared, 13 squared, and 14 squared. Let's say that we just, maybe last month, we were in class and we did a unit on parabolas. And so when I see that squared, I'm thinking of a certain kind of equation. Anybody, so, I mean, some of you might not have thought of this stuff for a long time, but.
Talking about like quadratic.
Here we go, okay, all right. So I wonder if I could use some variables to come up with some more knowledge about what's going on here. If this weren't a computational problem, but it was an algebra problem, would that help me?
But how do you define that?
Well,
Do you
that's,
have
yeah, that's
6
the
different
question.
variables, or do you have?
Well, are there some relationships between the numbers, especially in the numerator?
Plus 1, every 1.
X plus 1, and each one of them is square.
Okay, so what would that look like?
X
And I'm gonna lose
So
the
it'd be like
line.
X
squared
plus
plus-
X plus 1 squared plus X plus 2
I'm gonna
squared
try to capture this for the people online.
plus X plus 4 squared. Maybe.
Okay, let me catch up. So you had x squared
Yeah, x squared
plus,
x plus 1 squared
okay,
plus x plus 2 squared plus x plus 3 squared plus x plus 4 squared.
But if you're trying to figure out if they're equal to one another, you
Okay.
can put, like, the first one equals x plus 3 squared plus, you try to get them.
okay, so now we're gonna put it in the context of what Ms. Pink
Yeah,
told us to do, right?
Yes.
so this actually isn't gonna be a plus, but it's gonna be a
Equal sign.
equal. Okay, now what do you do?
How do you define the denominator in those terms?
Well,
Because
in
it has
this
to be-
case, it doesn't, we could just leave it as over 365, it doesn't matter. No, because we want to know about patterns that are happening with that sequence. The 365 kind of becomes irrelevant when we're looking for patterns. Initially, to come up with 2 as the answer is important, but when we're trying to find the 5-number sequence, it wouldn't matter if that was 365 or 1,080,000. It doesn't matter. Okay, so then what can we do?
Guess and check. Throw a number in there.
Say so.
You could throw a number in there if you wanted to, but that wouldn't be much different than what you were doing before,
Right.
it might not be. So if I solve for x, then I end up with x squared here, and there I get x squared plus 2x plus 1. You'll get this in Khan Academy this week, but just a quick review. Right? We always did binomial George in school, and everyone does FOIL now, but it's, you multiply first, last, and then inside and outside to get your answer. Plus x squared plus 4x plus 4 equals x squared plus 6x plus 9 plus x squared plus 8x plus 16. Yeah. But, so, let's say that you did have a unit where students were using FOIL to solve problems, and then you pose this problem to them. Some of them, because it was so close to the time frame where you're working on this, they're gonna see this square, and they're probably gonna go in some sort of direction like this. Maybe it won't even be an x, but maybe they'll think, well, 11 is 10 plus 1, so it's, instead of x plus 1, it's inside the parentheses 10 plus 1 squared. So they'll probably do things like that anyway. Because kids tend to focus on what they learned in the immediate past, right? All right, so here we end up with 1, 2, 3 x squares. And we have 3, and then we have 2 x's and 6 x plus 5 equals
2x squared plus 14x plus 14.
plus 25. Okay. Now what?
How you can combine like terms
And so what we're doing here
or the.
as a quick review is I want to get like 0 over here. I'm going to get rid of all those. So I'm going to subtract all of these from both sides. Subtract 2x squared from both sides and get 1x squared. Subtract 14x from both sides and get negative 8x. Subtract 25 from both sides and get negative 20. Okay. And then you have a choice as to how you're going to solve that. You could use the quadratic formula, or you could factor. You can factor. I didn't do this before we walked in, so they're going to tell me. I know it's going to be an x, and that's an x, and there's a plus and there's a minus. And 20. Yeah. And we want the 10 to be negative, right? To make that part bigger. So we get x equals negative 2 or x equals 10. Okay, what was x in the problem we had?
10.
So what do you suppose is the other x of the 5-number sequence? Okay, try that. Negative 2 squared plus negative 1 squared plus 0 squared plus 1 squared plus 2 squared. Are the first 3 terms the sum of the first 3 equal to the sum of the last 2? Yes. Okay. All right. So this is a perfect example of how problems can be at different levels, okay? So if this was something, if I wanted my students to make a connection to a quadratic equation that they would solve, I could provide hints as we're going along, you know, and encourage them to try different things. If you're already working with variables and equations, it doesn't seem all that crazy to me that you would suggest, well, could you try it with the variable and see if you can see a pattern that way. And usually if you've studied that content, they're going to go where they know the content that works for them anyway. So do you see how many ways that one problem, that one task could be used? It's really amazing what you can do with it. When on the surface, it just seems like a raw computational problem that couldn't even be approached mentally.
Is there another way to do it that you know of?
Yeah, I mean, you could find the sequence. So one of the roadblocks, and I heard others in the room talk about this, we tend to start with counting numbers. They were kind of, in our nature, we will either start with 0 or 1, not considering the negative numbers. So if I was using this with kids, I might say, well, why did you start at 0? Or why did you start at 1? Or is there another number that you can start with? You know, just encourage them to try new things. And they would quickly find the sequence if they would start in the negative numbers. It wouldn't take long at all. So, yeah, I mean,
I think everybody went up
yeah.
the first time.
Yeah, I mean, we don't tend to think about starting in a negative. And, you know, the way the problem is written, it kind of encourages the positive integers, so squares. That's
But
kind of
what I wonder is this the only two?
It is.
It is?
And why do we know it's the only two?
Because that's the only two answers right now.
I mean, this is, we solved the problem. There's no other alternative.
Yeah.
The sequence that starts with -2 and the sequence that starts with 10. Now, you could pose a problem, are there other powers that would have this property? Maybe they could look at powers of 3. If we have a sequence of 5 cubes, where the sum of the first 3 equals the sum of the last 2. I don't know that answer. But we could find out now that we know what we're doing. We could just make an equation and solve
So
it.
it's no longer a problem.
It's no longer a problem. It's no longer a problem. All right. Okay. So here's a question for you. The principles and standards, that's the 2000 National Council of Teachers Mathematics document, says, gives us example. Find out whether there are more boys than girls in the 4 second grade classrooms in a given school. Could that be a problem for a second grade student? Find out whether there are more boys than girls in the 4 second grade classrooms.
No. Because they can do survey and then, like what you said before, and they probably already had background knowledge of something that they've done similar to that. So they could go and count the kids in their class, count the kids in the other classes. So it really wouldn't be a problem.
Okay, so
Or many.
when would it be a problem? What kind of lack of background knowledge would need to be present in order for that to be a problem?
Skills, social skills, survey skills, typing in my classroom.
Right.
Like, it would be a problem in my
Access to
classroom, access
the
to other teachers.
information, like if you're a first grader and we want to find out about fifth grade, we don't know, we don't spend any time. You know,
So they wouldn't even have a
they don't have
pathway
any
into the
institution.
solution. Yeah. So in this case, if you have students who aren't confident of what it means to have more or less of something, then it would be a problem. What kinds of, if they didn't understand that I need to add the boys and add the girls and then look for the difference, what kinds of things would young students do? Would there be a way to solve this if you didn't know how to add and you didn't realize that being able to find more involves subtracting two numbers.
Did they do tally marks? Did they remember, right?
Yeah, so they're kind of matching one on one. For every boy, there's a girl, and I'm just matching them up, and then if there are more boys at the end of the line, I know that they're, I can count that. Okay. So that's not a problem. There are lots of word problems in second grade math curricula that would look very similar to that, but they're not a problem. And then it says, what about 10th grade? Is it a problem for 10th grade? No, as long as the data is there, that shouldn't be a problem at all for 10th grade, even though it would still be a word problem. The words have nothing to do with whether or not we're going to say that it's in fact a problem. All right, so these are some problem-solving strategies that you can always encourage your kids to use whenever they get stuck in their problem-solving. They could draw a picture. They could solve a similar but simpler problem. So if you're working with, we were doing the sequence of 5 square numbers, maybe you could ask them to look at, well, how would you do this if we were just using whole numbers without squaring them, just to get them in the habit of summing and comparing the numbers and then maybe moving up. Using a special case to find a pattern, that's sort of what we did for the math problem for this week. The reason typically I would bring up the problem from last week at the beginning of class, but we have 2 students who joined late who haven't done the problem yet, so I don't want to talk about it. And then I don't know if you noticed, but on the due date, I put June the 16th. So I didn't get all the problems in across the class, and I wondered if that was why. So that's fine. Just if you didn't turn it in, just turn it in when you can, and then we'll talk about it next week. But that was what we did. We were using special cases to find the pattern. So you use the calendar to get the 3x3 square, and then hopefully found some sort of pattern growing out of those squares as you move them around the calendar. Working backwards, which we talked about today, coming up with the answer, and then thinking about it in reverse can help you build mathematical knowledge. And then adopting a different point of view. I think that often comes from hearing others think through the problem, that idea of communicating the strategies and thinking about the context of the problem in different ways. Okay? So when we were working on the sequence problem, the teacher can help that along. You can give appropriate hints and help students see the problem from a different point of view. And that's okay, without telling them the answer. That's the hard part. The sweet little faces. I don't know what to do next. Sometimes not so sweet little faces. All right, I think we're almost done with the slides, but this one, I wanted to talk a little bit before we get into our problem solving about student beliefs and how we can impact student beliefs. What do you think? How important is a student's own conception of themselves as a problem solver and how well they can problem solve? Incredibly. So how can we go about impacting that in a positive way?
Foster an environment where mistakes are not called out, but yet it's a learning opportunity.
Or if there are mistakes, question them, make them think about why is that a mistake, or how can I fix that, or talking to each other and figuring out, why was that a mistake? Well, how can we go about a different way to see if we get another mistake or if we get a correct path?
Yeah.
Give them multiple strategies so they're not just trying to figure out one way that's not working for them.
Picking out the mistakes that are very common and going over those, because there are certain things, and we know as teachers that somebody's going to pick this answer, and this is what they're going to do. So going over those perfect mistakes is what I've always called them. So.
I always remember the first time teaching fractions with kids, if I give them the fraction 1/2 plus 1/2, and I'm thinking, oh my gosh, this is so easy. They're going to know what that is. And then they give me an answer like this. So I think Tabitha is right. That's something that you could kind of investigate in the lesson itself, so they don't make those kinds of mistakes. And yeah, I agree. Why do you think that is, by the way?
Because that's what they know.
I'm sorry.
That's what they've been taught, add
Yeah.
number.
They're using whole number thinking with
I
fractions.
think too, like, especially if they're, like, even our kids make these mistakes in middle school. Because they get that mixed up with multiplying. You multiply straight across, and then when you add, you don't. So I think that they get, a lot of times they get those things up.
Yeah.
And then the whole KFC, I mean, that's.
And then when you get to the division and you do the.
Yeah, well, that's what we call it.
Multiply, like, oh.
That's what we call it, oh, KFC.
What's KFC?
Keep it, flip it, change it. And I
That's
say,
what's in
see,
there?
and I go, and I always say, keep your finger looking good. Sometimes. You gotta keep your finger looking good, and then they go and say,
I had never, KFC.
keep it, flip it, and change it.
All right. What, anything else that would impact beliefs?
You have to give them opportunities to be successful, to build the confidence in the first place. So you have to foster situations where they can do it well enough that they have the confidence to do it independently, or even with your help still, but like, they have to be able to think that they can.
Right. That's so important. And I think that a lot of times as classroom teachers, we might forget that even if a child doesn't have an IEP, that doesn't mean that the child doesn't need some kind of accommodation or modification. I know in BCSC with the with UDL, we try to build that in, but still, I mean, every student in the classroom has different needs, and if they continually fail at everything they do mathematically, their belief is going to be, I can't do math. And we wouldn't accept that if they said they can't read. Well, we want to teach you to read, never going to read. But oh yeah, if I can't do math, that's perfectly fine. It doesn't matter. Okay. The other thing that I think is important, it's more subtle, but what messages we give off as problem solvers, okay? That we're okay with making mistakes. And sometimes that means making an intentional mistake and letting them catch you and showing how you handle that situation is important. Letting them understand that you're a problem solver and that you're curious and that you really might know how this math problem works, not just them. So it's the message that we give as problem solvers too that helps impact those beliefs. And the messages we send them in feedback, I don't believe that you should say everything a child does is great, right? There are those teachers, I know, that no matter what, oh, that's perfect, think of this way. No, but the kids need to know that what they're doing is valued in the classroom, and they need to feel as if they're respected as a contributor in the classroom. So those messages that we give have a lot to do with it too. I've done a lot of student teaching, supervising, a lot. And I've been in math classrooms and general ed classrooms, and I've seen a lot of different variances, I guess, between how the classroom teacher would teach in a certain subject area versus another. And one of the things that always intrigues me is the difference between a teacher who thinks he or she is not good at math, how they teach math, versus how they might teach social studies or language. It's amazing. So I don't know, I think we kind of perpetuate that sometimes. And if you don't see yourself as a mathematician, how can your kids? And it's kind of funny. I love math so much. I think you all know that. This is the last thing I wanted to share, and I thought this chart was nice because it really helps us understand how we can transition from a classroom where problem solving isn't really at the forefront to a classroom where it is. And there's 4 levels that are defined. And the first one, it's when students really have no understanding what problem solving is. So they're looking for a structure that they can replicate. They're just trying to get to the answer. They're going to replicate whatever structure you give them. And then in this kind of classroom, the teacher assumes the role of the model. So you might present a problem, help them solve it. That's the model for the problem solving, and then they go and do the same thing at their desk. The second level is when students understand the meaning of the problem or strategy and the structure of the problem. They're able to follow someone else's solution and can often suggest strategies to be tried for problems similar to those they have seen before. Although they will participate actively in group problem solving activities or instructional episodes, many feel insecure about independent problem solving. And you probably have seen this in groups before. If you have kids solve problems in groups, there's always a student who might be more comfortable in contributing in the group situation, but then if he or she is on an individual basis, may not have those skills. And then the teacher, or even sometimes the other students, are really acting as the crutch. So they're taking up, they're giving in all the skills that that particular student hasn't developed yet to the problem solving situation. The third level is when they begin to feel comfortable with problems. They suggest strategies different from those they have used. They understand and appreciate the problem, may have multiple solutions, and that no solution may be perfectly good. And that's when the teacher becomes the problem provider. So you're choosing problems purposefully to have them engage with them in this way. And the last one is what we would all strive for, and that's when students are able to select appropriate strategies for most problems encountered and are successful in finding solutions. Much of the time, they suggest variations of old problems and are constantly searching for novel problems to challenge themselves and others, and that's when the teacher is the facilitator. And I've seen this work very well in classrooms before, when students will say, oh, this problem is sort of like what we did last week when we solved the problem about the playground or whatever. So they start making connections, and through that, they come up with solution paths that they can try, and they feel confident enough to take that risk to do it. So that's what we want, but that kind of shows you the evolution, how we can make that happen. All right. Any questions about this? You are not tested on this material at all. It's for your information, and since you're here in class, you don't have to summarize it. Those of us online will. But what I want to end with is some problems. I'm going to give each table a sheet of poster paper. This is just, you can doodle all you want on this, doesn't matter. You can keep it if you want, or you can pitch it, whatever you want to do. If you need more pieces, you can get them. I have some markers up here I can give you if you want to have the markers on this. And then we're going to take maybe 15, 20 minutes to work together, and then we're going to stop. And you guys can take off on your own and finish up. And I'll just leave you up here. I've got to set up the problem. I'm trying to figure out how to do that on this recording. You want markers? Alright, so let me see if I can get this on camera. Actually, let me try it. All right, so the problem is we're imagining staircases, and we want to find out from our building blocks how many building blocks we need for each set of staircases. So if I have one step in my staircase, I'm just going to have, think about those cinder blocks, you know? I'm just going to have one block. That's easy. I need one. What if I have two steps? How many blocks would I need? So I need two on the bottom and stack one here, right? Looks awful. All right. What about 3 steps?
3 on the bottom, 2 in the middle, 1 on top.
Okay. Okay. And then for the fourth, I won't draw it, but what would it be? One more. Right, okay, so there's a pattern established there, right? Could you figure out how many I would need if I wanted 10 steps? Start there. How many blocks would I need for 10 steps?
Like, are you talking about like stuff like this, like individual stuff?
Yeah, so if you can imagine, if we were building steps with cinder blocks, and I wanted a step just to lead from the side of my house to the door, I might just need one, okay? But let's say I have a deck, and I'm gonna need maybe 3 or more. So let's say I needed 10. So I needed to build a staircase with 10 steps leading up to something higher. How many of those blocks would I need altogether if I needed 10 steps in my staircase?
Too many.
Too many. Okay, I was not meant to draw on an electronic whiteboard.
Probably.
So from what we did in the first 4 staircases, is there some sort of pattern that you found that you could find the total number of bricks?
The highest step has the same number of blocks, and then each one before that is one number less.
Okay. So I was looking here, is there a pattern in these totals?
So you're adding 2, 3, 4.
Yeah, you kind of see like,
Yeah.
That's 2.
it's sort of like the one before plus the bottom row, right? 3 plus 3 is 6, 6 plus 4 is 10. If I don't want to use the sequence, and I know that I have 10 on the bottom row for 10 steps, what would I do to find the total? 10 on the bottom, then, so 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Okay, so there's some things going on that could help us find the number. What happens if I want a staircase with 152 steps? Or 1,000 steps? Or 3 million steps?
Really long addition problem.
It could be a really long addition problem, but is there something that we can come up with as a rule that no matter how many steps that I want in my staircase, I can use my rule to find the answer without doing repeated additions? That's what I want you to think about for this week. Okay. And your goal in problem solving is exploring. To be quite honest, I don't care if you come up with the right answer. I want you to explore with the numbers and find out what you can about them. So the goal would be, beyond what we found here, to come up with some sort of rule that would help you to arrive at the number of blocks in the staircase, no matter how many steps you want. Okay. So I'll tell you, there is a rule that exists for this. So there is a rule to be found, okay? So no matter what I would choose, I could input the number that I choose into that rule and come up with the number of steps. As you're doing this, think about how you would encourage your own students to keep going in their problem solving. If you posed a problem to them and they didn't have a clear solution path, what would you ask them to do? Ask yourself to do that.
What would I tell them to do?
Yeah.
I think that it's easier to say if you know the end.
That's true. But what kinds of things would you tell them to do?
I told them to keep, like, you proposed us to do 10. Well, we all jumped to 10 because we already knew how to get there. But, like, right now I'm trying to go back and go through those 4 through 10 to see what patterns do I see in those, blocks that I'm missing because I just jumped to the answer.
Right.
And so I encourage them to go back and make diagrams and figure out numbers and see if they see any patterns with those lower numbers in order to find their rule.
So let's say that they have everything drawn out. They're doing something similar to this. They're building their staircases and there's some numbers there. What other kinds of things could you tell them to do with the numbers? Who had lead bread? What did you always say?
A lot
That
of
was
things.
a long time ago.
There's a lot of.
Make a
Table.
Make a table, make
Like a chart.
a table, make a chart.
yeah, so that, I mean, that might help, looking at the
That's
numbers in different
One of the
ways.
things I was thinking was that, like, one of the things that I did in her class was I wrote everything down. I didn't, even if it was a simple step, I wrote it down because there's oftentimes those things that you don't consider and you get so complacent with the little stuff that you skip it.
Right.
So,
Yeah, that's true.
okay, so we make a table of the values. Like 1, 2,
So one of the things that you're probably going to find early in your problem solving, that there's sort of a recursive rule that you can come up with, where you can't jump directly to the number of stairs, but you can use information about other stairs to get to it. So that, I mean, if you arrive at that, that's a good start.
7, 20, 8, 36, 9, 45, 10, 55.
So how could you make that into a rule? What would you say?
Number of stairs is going to be the previous number plus the current. The number of blocks of the previous step.
Okay, so how could you make that into a mathematical rule? What would that look like? That's perfect. What I mean, right?
I don't know.
So N would be your current step, the steps you're working on,
Yeah, and is the,
number of.
but I think that we have, the step number.
Okay. So like on my third one, N would be 3.
Yeah, right.
Okay.
And you have to add that, so we n plus n minus, well, that's the total number of the previous step. And so we do the number of blocks in the previous step.
Yeah, so it's not the same as N plus, is it the same as N plus? Or N plus N minus 1? Where does that?
See, that's the part I get hung up on.
Okay, so I'm kind of thinking, you've got, if I overlaid that on this, what would I have? So I would have this one. I'm just gonna make a mark on, whoops, that's wrong. Making a mark. So if I were to overlay that on there, I have 3 there. And what happens if I overlay? So that's gonna be, then you're adding 4 there.
Well, we're generalizing it. So another pattern is if you start with X, and the next one is X plus 1, and the next one is 2X plus 2. The pattern keeps going. I haven't gotten farther than that, but I've figured out that that's the pattern. Do that.
Okay, say that one more time, so right here, Chef.
Okay, so if we start at 1 as X, so the number of sets is X, and the next solution is X plus 1, then you have 2X plus 2, 3X plus 3, 4X plus 4, and the pattern continues. 5X and 5X plus 5. So I made a chart, and then those are the patterns that I've already noticed.
That's interesting, isn't it?
Because we've all gotten hung up on, we know it's the number of steps plus the previous one, so I was trying to generalize it more. I brought them a lot, but I don't know.
Any other ideas that you're seeing that you want to share with everyone? Will the back group talk a little bit about what you did, because I think they might have maybe too.
We just made a chart and put the 1, 2, 3, 4, 5 all the way down to 10, and then we were figuring out the number of blocks that we needed on the other side, and we're noticing a pattern that it's increasing by 1. So plus 2, plus 3, plus 4, plus 5, plus 6, so that we can see that away.
So the total number of blocks in each subsequent staircase is increasing in a sequence that starts, a whole number sequence that starts with 1.
Yeah.
Well, yeah, I guess we had no steps.
Right.
All right, we have two interesting patterns going on.
I've also noticed that on my pattern, if it's like the 2x, those are odd steps. 2x plus 2 is an even step, and when I'm multiplying and when I'm adding together equals that number of steps. So 2x plus 2 equals my 4th step. 3x plus 3 equals my 6th step.
Do you see what she's, so she's looking at that as x, and then this one is 2x. And so if we were,
2x plus,
if we skipped to the next one, it would be 3x, or we
Yeah.
skip one and go to the next one, would be 3x. And then the even numbers are plus, what, 2x plus 1?
that one was x plus 1. And then the next one was 2x plus 2. So that 2x, so that 2 plus the 2 got my 4th step. So like x plus 1, so 1x. So 1 and 1 is my 2nd step.
Interesting.
My brain knows.
Uh-huh. That's good. So your pattern follows the odd number of stairs and the even number of stairs.
Yeah.
Anything else to add? Okay, so the things that we've talked about, we started with thinking about the number of steps previously. That could be a pattern, right? So 3 to get my, this is misleading because this is really 2 steps with 3 blocks. So I'm taking what I had before and I'm adding my step, right? What I had before here was 3 and I'm adding 3 more to get 6. In the next one, I have what I had here and I'm adding 4 more to get 10. Right, so that leads to the pattern that we write down. And then what Samantha has deals with the odd number of steps versus the even number of steps. So those are 2 things to start with. And see if you can find any way that you can represent that pattern in one rule that would work for any number of steps. Don't spend a lot of time on this, but give it some thought. You know, if you have an extra half hour this week, you can sit down and revisit it and then write up your strategy and submit it. And then we'll talk about it next week. Oh, Samantha's got something else. I think got it. What'd you find?
Like using my pattern. So for 100 steps, it'd be 5,050 steps. For 99 steps would be 4,950. Following rule that I just said, I generally answered more.
Okay. I don't know how many are gonna finish.
Right, but I'm just saying, like,
Yeah,
following
okay.
that rule,
All right, so
it
you
followed,
use-
and then I checked it with other steps, and the same rule
Okay.
kept pattern.
So as long as you know if it's an odd or an even, you think you have a rule that works. That's good. Listen, I've never seen somebody do it that way before. You're the very first. I've used this problem so many times. We have, for 2 years, I worked with a group of teachers from South Korea who came to IU Bloomington. You know, Korean education system is probably amongst the best in the entire world. But they came to IU Bloomington to learn how we teach math. I don't know why, but we did this problem, and they came up with an answer very quickly, but it was very regimented. They didn't explore it all. They just came up with an answer. And I've worked with teachers all over the southeastern part of the state using this problem. I've never seen anything like this before. You're 1 in a million, literally. Well, that's good. Any other tidbits to add before we set you loose on your own? If you think of something and you want to connect with a classmate during the week, that's perfectly fine too. And you know, your write-up, as long as it's My magic number is usually 250 words, so write up what you did this week on that problem, what you think is going on. Okay? You're welcome to stay here as long as you want if you want to solve together, but otherwise, we are done for this week. Next week is midterm, and I will have your problem sets ready. I'm just so happy to see everyone. Taking me back in time. I had, Greg is in our, has been in our monthly. Are you?
Yeah.
So I got him from that for our monthly meetings, and everyone else was my student here at IUC.
I'm interpretive.
Yeah. Okay, well, for those of you who can be here next week, I'll see you. Otherwise, I will record and post. So. Oh, you have someone from Shelbyville who's participating. So will she be coming?
That's my first class.
I'd like to meet
The
her.
next was one.
Make her come.
And then
She got, her kids are crazy, so that's good.
Okay, we'll try.
Oh,
Okay, so think of this again. So think of this.
And then kids are bigger children. Give them an iPad. Keep them busy.
They're little.
Okay.
Those are cute. Yeah, I'm gonna try to get her to send us
There's
that.
3 blocks in there.
Right here. Right. So 2, put that in, 2,